So today we are having Daniel Stern from University of Toronto, who will talk to us about Minmax harmonic maps and extremal metrics for Laplacian eigenvalues. So Daniel, you have the floor, and thank you very much.
Great. Well, thanks a lot for the invitation. I've been really enjoying this seminar series over the course of the quarantine, so it's nice to get a chance to speak. Yeah, so this is about using min-max methods to probe some extremal problems for Laplacian eigenvalues, and this is all joined with Mikhail Karpukhin at UC Irvine. Okay. So, I mean, broadly the kind of problems we're looking at, we've already heard a lot about from Josip Polterovich earlier in the seminar, and from Henrik Mathiasen before that. So we're interested in shape optimization problems for Laplacian eigenvalues on closed surfaces. Okay. So we're going to be on two-dimensional closed surfaces. We're looking at the Laplacian with positive spectrum. Okay, and we're thinking about the normalized eigenvalues of the Laplacian. So we multiply by the area to get a scale invariant quantity. And we're interested in this fairly classical isoperimetric problem. So we're interested in first just finding upper bounds for these eigenvalues over all metrics, either a fixed conformal type or more strongly over all metrics on any surface of fixed topology. Okay, and then we're also interested in then identifying, or at least characterizing, giving some description of maximizing metrics, or if a maximizing metric doesn't exist, understanding maximizing sequences of metrics saturating these bounds. Right? So there's this isoperimetric problem that we've heard about in previous talks. Okay, so in particular, given the closed surface in the conformal class, we can define these so-called conformal eigenvalues by taking the supremum of the normalized eigenvalues over all conformal metrics. And similarly, we can define these topological eigenvalues by taking the supremum over all metrics. Okay, so I mean, of course, shape optimization for eigenvalues in other contexts goes back to the 19th century, but for closed surfaces, the results begin with this classic result of Hirsch in 1970, which tells us that the round metric on S2 maximizes the first eigenvalue among all metrics on the two-sphere. Okay, so I think this is well known to most of you, but let's quickly recall the proof because it'll come in play later. Okay, so the idea is if we have any metric on the two-sphere, we know we can always find some conformal diffeomorphism to the standard. Okay, and moreover, we can always compose that with another conformal diffeomorphism of the standard structure. Okay, such that the components of that map, the conformal map, are balanced in the sense that each component has zero average. Okay, so this is this Hirsch trick. Okay, so why does that help us? Well, by the variational characterization of the first eigenvalue for the Rayleigh quotient, we know then that the energy of each component is bounded below by the first eigenvalue times its L2 norm squared, right? But in particular, since we have a sphere-valued map, then summing over the L2 norm of these components, we get the area of S2 coming out, right? The area of our metric. So in particular, we see that the area of our image, which is exactly just Dirichlet energy, we get that twice the area of the standard S2 is bounded below by lambda1 of whatever metric we're looking at to begin with times the area, exactly this normalized first eigenvalue. Okay, so we get this classic result of Hirsch. All right. Okay, so the same balancing trick for maps to S2 was applied in a slightly more general context by Yang and Yao to get some non-sharp upper bounds on lambda1 that hold for any closed orientable surface. In particular, they show that these capital lambda1s are at least finite. Okay, but then the same trick was refined a little bit later by Li and Yao, okay, who observed that you could use the same balancing trick for maps to higher dimensional spheres. Okay, and this leads us to the notion of conformal volume. Okay, so in particular, given some branched conformal immersion from our surface into a higher dimensional sphere, again, we can always find some conformal automorphism of the standard higher dimensional sphere, such that after composition, each of those component functions is balanced, which again makes it a valid test function for the Rayleigh quotient in estimating the first eigenvalue. And so again, this Hirsch argument shows us that the area of the image, where area is taken with some multiplicity, is equal to the energy, which is just bounded below again by half this normalized first eigenvalue. Okay. So in particular, building on this, Li and Yao define this nth conformal volume, where you look at fixing some branched conformal immersion. You look at the supremum over all conformal automorphisms of the sphere, of the energy of this composition, and then you take the infimum over all branch conformal immersions. Okay. And so what they observe, which we just saw, right, by this Hirsch trick, is that for any conformal structure, twice the conformal volume is an upper bound for the normalized first eigenvalue. Okay, and moreover, it's not too hard to see that equality holds if and only if this metric G is induced by a minimal immersion, maybe a branch minimal immersion into this Sn by first eigenfunctions. Okay. So for example, since the coordinates of the minimal embedding of Rp2 into S4 are first eigenfunctions, this gave the first characterization of the round metric as the maximizer for the first eigenvalue on Rp2, right? And moreover, this isn't as relevant to the spectral story, but it's illegal to talk about conformal volume without mentioning it. The conformal volume is also giving a lower bound for the Willmore energy of conformal immersions into the n-sphere, which is linking in particular this problem of maximizing lambda1 to minimization of the Willmore functional. It's a whole other story, but important. Okay. All right, so in the decades since then, there's been a big literature growing up around this. And I'm just going to give a brief overview because we already had this very nice one by Josip Polterovich a few weeks ago. So if you want a nice overview, you can go back and look at his slides or video. All right, but in particular, some highlights are Korevar's result in the early 90s, showing that in fact the kth eigenvalues satisfy a linear upper bound, depending only on topology as well. Okay, so in particular, these lambda k's are always finite. All right, and another key result is this result of Nadarashvili's from 96, in which he proved this conjecture of Berger, saying that the flat equilateral torus is the maximizer for lambda1 among all metrics on the 2 torus. Okay, and one thing that distinguished this from some of these earlier characterizations of maximal metrics is it actually relied on some existence theory for maximizers. Okay, so particularly you have to first show that some maximizing metric exists, you characterize it, and then say that this allows you to rule out most possibilities. Okay. So in particular, in light of this result, the existence theory has kind of exploded as a subject, maximizing metrics. And really in the last decade, it's been, there have been tremendous improvements. So for this talk, we're going to be particularly interested in the existence theory for conformally maximal metrics, again, similar to Josip Polterovich's talk. Okay, so as we learned a few weeks ago, by work of Petrides and also Nadarashvili-Cyr, and Karpukhin, Nadarashvili, Penskoy, and Polterovich, the existence theory for conformal maximizers is pretty well understood at this point. So in general, what do we know? Okay, so we always know that that the kth conformal eigenvalue is bounded below by the k-1 plus some 8 pi, whereas 8 pi is coming from sort of a round sphere bubbling up. Okay, for each k bigger. And moreover, with strict inequality, so if we're strictly greater than the previous eigenvalue plus 8 pi, then this implies that in fact there is a maximizing metric where we allow that this has some finite collection of conical singularities. And this metric admits a map into some higher dimensional sphere by kth eigenfunctions. Okay? Whereas if we do have equality, then we think of this as coming from some degenerating sequence of metrics where there's some piece bubbling up to a round sphere. And moreover, if k is 1, so we're looking at the first eigenvalue, then if m is not S2, then the strict inequality lambda1 strictly greater than 8 pi always holds. It's a result of the treatise. And so in particular, every conformal class, at least we know, contains a lambda1 maximizing metric. Okay, so for the first eigenvalue, there's a really robust existence theory. Okay, so that's the situation for conformal maximal metrics. But this then feeds into the structure for topological maximizers. Okay, and so building on these results, Matthiasen and Sippert were able to show that in fact there are globally maximizing metrics for lambda1 among all metrics without a fixed conformal class. And so now this is reduced to a finite dimensional problem of analyzing how conformal classes might degenerate along a maximizing sequence. Okay. So in particular, what I haven't said here, but that comes out is that this is really related to this theory of harmonic maps. Okay, so if we fix a conformal structure, then maximizing this lambda k is giving rise to a harmonic sphere-valued map whose energy is exactly half this conformal eigenvalue lambda k. All right, so certainly if we have a map by eigenfunctions with common eigenvalue, this has to be harmonic, but then this being harmonic is a condition which is conformally invariant, so it makes sense for every metric in the class. Okay, and moreover, given this harmonic map in any metric, we recover the maximizing metric just by setting it to be, say, dp squared times g. Okay. So just to recall, a harmonic map just refers to any map, in this case to the sphere, which is a critical point of the Dirichlet energy among sphere-valued maps, so among the constraint that is taking values in the n sphere. Okay, and equivalently, this is just that it satisfies this PDE, just saying that the Laplacian of phi as a map to Rn plus 1 is proportional to phi, and in fact, that's enough to conclude that this proportionality factor has to be dp squared. Okay. So those are harmonic maps. All right, so we have this maximization of eigenvalues giving rise to this distinguished collection of harmonic maps from our surface to high-dimensional spheres, and this is working for any conformal class. This is a pretty robust construction. And moreover, if we maximize among all conformal classes, we're getting minimal surfaces, still more special. Okay, but in particular, as critical points of the Dirichlet energy, we know that harmonic maps arise most naturally from variational methods for the Dirichlet energy. So we expect that, if we have somehow a natural harmonic map from a surface into a sphere, say, then the expectation is that, in fact, there's some topology in an appropriate space of maps to the sphere, such that some Morse theoretic reasoning is forcing the existence of this critical point. Okay? And somehow the starting point for this project with Misha is a question of whether these harmonic maps associated to maximization of these eigenvalues actually also have a nice characterization in terms of just the more classical Morse theory or Minmax methods for the Dirichlet energy on sphere-valued maps. Okay? And the answer turns out to be yes, at least for the first two eigenvalues. So for these lambda 1 and lambda 2 in any conformal class, we can identify a natural min-max construction for sphere-valued harmonic maps, which recovers these maximizing metrics for the eigenvalue problem. So that's kind of fun. But moreover, this allows us to get new information about these quantities, right? So in particular, since we're not going to be finding these maximizing metrics by direct methods, but by kind of relating it to this external problem, we're able to show that, in fact, these maximizing metrics maximize first eigenvalues for a much broader class of geometric pseudo-differential operators, and some that have very natural geometric interest. So it gives us a little bit more information in those cases. Okay. All right, so let's go through a bit of the min-max construction. So the starting point is really the conformal volume store. Okay. So if n is bigger than or equal to 2, we're going to be thinking about weakly continuous families of maps parameterized by the unit n plus 1 ball. Okay, so they're going to be maps sending the unit n plus 1 ball into maps from M to the sphere, okay, of finite energy. And we have a little boundary condition here, which says that for a point in the boundary of the unit n plus 1 ball, this map f sub a is just the identity map to this constant a. Excuse me, not the identity map, it's just the constant map to this point a. Okay. So for example, if phi is some conformal automorphism, and we excuse some branch conformal immersion into the sphere, and we compose with these family of conformal dilations of the n sphere, okay, then this is going to give us such a map. And note that these aren't going to be strongly continuous. Okay, so there's going to be some bubbling behavior as A escapes to the boundary. So it's important that we're requiring only weakly continuous here. All right, but these maps are going to give us a family like this. And more of a note that these G sub A, these conformal dilations, are going to generate the conformal automorphisms of the n sphere up to isometries. Okay, so in particular, when we're looking at the infimum overall phi and the supremum overall A of these energies, this is going to give us exactly the nth conformal volume of the n. Yeah. Okay. So in particular, suppose we have any family satisfying these conditions, right? So if we look at the map, just sending each point to the average of the associated sphere-valued map, well, this is just giving us a map from the n plus 1 ball into Rn plus 1. It's going to be continuous because we require that these are at least weakly continuous families, right? And in particular, it restricts the identity on the boundary sphere. So it's just sending the Sn into itself by the identity, right? So just by elementary topology, the identity isn't null homotopic, so there has to be some 0 somewhere inside. Okay, so again, we have this Hirsch trick, right? Telling us that, well, for this A, then we know that the energy is bounded below in terms of the first eigenvalue. And so in particular, if we define a min-max energy by taking the infimum over all such families and the supremum over each point in the n+1 ball of the energy, then it's easy to see that this normalized first eigenvalue is bounded above by twice the min-max energy. Okay. And moreover, since the Dirichlet energy is conformally invariant, it's easy to see that this min-max energy, which is just defined in terms of the Dirichlet energy, is conformally invariant as well. Right? So this min-max energy defines this nice conformal invariant, which sits in between first eigenvalue on one side, the conformal eigenvalue, and the conformal volume on the other. Okay. All right, so that's the intuitive definition of these min-max energies. In practice, we're going to need a slightly different one because we want to actually say that these min-max energies correspond to critical points of the Dirichlet energy, the harmonic maps. Okay, and so to do this, we need a little bit more structure. All right, so let me just give you a quick cartoon recap of how min-max methods work. If you don't bathe in it every day, it might be something that we don't think about. Okay, so the cartoon version of min-max methods. So what do we need if we want to construct critical points via min-max methods? So if we want kind of classical min-max methods to work, first what we'd like is something like a reasonably smooth, at least C1, C2 is nicer for the kind of applications we're using. Okay, some nice, reasonably smooth functional on something like a Hilbert manifold. And maybe you can relax this to a Banach manifold or something, but Hilbert manifold is nicer. Okay, and then we'll have some non-trivial family of compact subsets of the space X. Okay, and we're going to ask that they're preserved by the gradient flow of this function f. Okay, so we at least need things to be nice enough that some kind of gradient flow is defined. Okay, so if X is, say, a compact finite dimensional manifold, this is enough. But since we're going to be interested more often in infinite dimensional situations, we need also this additional compactness condition on F, called the Laplacian condition, which tells us that for any sequence of points in the space X, such that the gradient is vanishing in operator norm, right? And if we have that f of these points is bounded, then we want to know that any such sequence has a convergent subsequence. Somehow having vanishing gradient in the limit is enough to force some convergence. Okay. So modulo some technical points, and there's a lot of technical points. If these three conditions are satisfied, then this min-max quantity, given by taking the infimum over all these families in gamma, and the max over each point, such a family of this f, then this is actually a critical value of the functional. Okay, so just a quick reminder, what's the idea here? We know that we can always find some family A getting arbitrarily close to this value C by definition, whose max is getting arbitrarily close, right? But we also know we can act on these by the gradient flow to decrease the energy. Okay? But the fact that we can't get below this value C is somehow telling us that no matter how much we run the gradient flow on these families, we can't push past this value. And so modulo a lot of work, the fact that the gradient flow is getting stuck is telling us there has to be a critical point at that value. Okay, and to make that precise in dimensions, that's where this Laplacian condition comes in. So that's the intuition. So in particular, we need nice enough structures to have good notions of things like gradient flow and derivatives of these functions and so on. Okay. Okay, on the other hand, the min-max energies we were defining, we were somehow working on this space of W12 maps restricted to take values in Sn, which is a very nonlinear constraint, right? And moreover, we were kind of interested in families that were continuous with respect to the weak topology, okay? So this space W12 of M to Sn, whether you're giving it the weak topology or even the strong W12 topology, it's really not going to be any kind of Banach or Hilbert manifold. Okay, and the Dirichlet energy is certainly not going to be a smooth or Laplacian functional on this space. Okay, so we can't just appeal to standard min-max theory and conclude that there is some nice harmonic map popping out as a critical point with this energy level. Okay, so we need some kind of regularization. But there's a nice one. So what's the idea? Well, we're thinking of defining this min-max energy in terms of these weakly continuous families taking values in the sphere. So instead, we're going to think about mollifying these weakly continuous families, okay, to get continuous families of maps into W12 with M taking values in Rn+1. Okay, if we're mollifying, then we sacrifice this nonlinear condition of taking values in the sphere. Okay, but they'll still have to lie close to the sphere in an integral sense, in an LP sense. Right? So in particular, given some epsilon greater than 0, and some map now taking values in Rn plus 1. We're going to consider these Ginzburg-Landau type energies, which have a long history I won't go into here. Or what are we taking? We're taking a map, we're spitting out the Dirichlet energy, plus this nonlinear potential term. Okay, so note that if our map F, we're taking values in the sphere already, well then this potential term just vanishes because F has norm 1 everywhere. And so we'd just be recovering the Dirichlet energy on sphere valued maps. If we're not sphere valued, well now this potential term is going to penalize us for taking values far from the sphere, and it's going to do so more and more harshly as this epsilon gets small. And the precise form of this energy doesn't matter too much. The point is that we have this penalization of this type. Okay. And a nice feature of this is that it really is a good approximation for the harmonic map problem, in the sense that critical points of bounded energy do converge to harmonic maps as epsilon goes to 0 modulo some bubbling behavior. So doing variational theory with this, guys, is in some sense a reasonable approximation of doing variational methods directly for the Dirichlet energy. Okay. Okay, so now we just define sort of a perturbation of the setup we had before. So if we denote by gamma n of m the collection of all continuous families, now we can ask that they're strongly continuous, of maps from the unit n plus 1 ball into W12 of m into Rn plus 1. And we again require this boundary condition that Fa is identically A for A in the boundary Sn. Well, then we just define these perturbed min-max energies E and epsilon to be the infimum over all such F, with the max over all these points in the n plus 1 ball of this energy, okay, this perturbed energy. And then we define this min-max energy E sub n to just be the limit as epsilon goes to 0 of these guys, which is the same as the supremum over all positive epsilon. Okay. And note that for fixed epsilon, these are no longer conformally invariant energies. And so neither are these E and epsilon conformally invariant min-max energies. But in the limit as epsilon goes to 0, it's easy to see that you recover conformal invariance. Okay. So any questions so far about the definition of these energies?
So why is it that this time you can consider strongly continuous families rather than only weakly continuous ones? Is it just a matter of the modification process?
Exactly. So when we mollify with this, this is going to take some weakly continuous thing, like say the conformal automorphism thing that we were starting with, right? And by mollifying uniformly, we get a strongly continuous family into W12. Okay.
So I also have a question, Alexandre here. So in this limit, you don't recover the initial energy, right? It's still a new object.
Yeah, let's see. So certainly it's going to be bounded above by the initial energy, okay, by some mollification. And intuitively, one expects it to coincide. And it certainly seems possible that, you know, with enough sweat, you could show that they coincide in most cases if you really wanted to. But I mean, somehow this turns out to, this does everything you want it to anyway. So, okay.
So I have another question on the slide before. You said that W12 from the surface to Sn is not a Hilbert manifold.
That's right.
I see that it's not a linear subspace because the condition is not linear. Mm-hmm. But how do you know it's not something that could have charts on it and being a Hilbert manifold for some atlas on it?
Yeah, let's see. I mean, so this is sort of a classical fact. It's so certainly W1P for P bigger than 2 is going to have a nice manifold structure. Okay, it's going to be a, you know, in that case a Banach manifold, but still a manifold. And if you're doing a Sachs-Uhlenbeck type perturbation of a harmonic map problem, you're taking advantage of precisely this fact that for P strictly bigger than 2, you have a nice manifold structure. And in particular, it's essentially the same structure up to homotopies as just looking at, you know, C0 or C alpha from M to Sn. Mm-hmm. Okay. I mean, in terms of a nice, concise argument why you can't get some nice charts, I can't say, but I mean, it has to do with the fact that you're at the critical value for sub-Leth embedding.
Okay.
Okay.
Yeah, thank you.
You're welcome. Okay. All right, so in any case, via this little perturbation procedure, we get another nice little definition of these ENs. And what's nice about these epsilon energies is they're kind of clearly nice, smooth C1 and even C2 functionals on what's now just a simple Hilbert space, right? It's W12 taking values in Rn plus 1. Okay, and it's easy to check that these inequalities still hold. So for our conformal families, we can just mollify and get competitors which give us the upper bound on this new min-max energy E sub n. And for the Hirsch trick, well, now we're not getting families which are precisely Sn valued, but they're going to be arbitrarily close to Sn valued in at least an L2 sense. And that's still good enough to apply this Hirsch trick in the limit and say that we're going to be bounded below by this conformal eigenvalue. Okay. All right, so in particular, since these are nice smooth functionals, they also are not hard to check, satisfy a Palais-Snell condition, this compactness condition for critical sequences I was pointing to before. It's not hard to see that these energies, in fact, correspond to honest critical points of this functional. Okay, and moreover, since they're C2 functionals, we can argue that they're going to have Morse index for this energy at most n plus 1. So, right, so these are critical points. They're defined by this min-max procedure telling us that they're somehow intuitively they're the maximum in an n plus 1 parameter family, but this family minimizes everywhere else. So it's not surprising that the second order, they should look like they're maximizing in an n plus 1 space and then minimizing in directions orthogonal to this. Okay, so they have Morse index at most n plus 1.
Can I ask another question?
Go for it.
Do you have all critical points like this, or is it a subset of the critical points?
You're asking if all critical points of these functionals
yeah.
I'd be inclined to say no. I mean, let's see. I mean, as a general rule, you don't expect to produce all critical points from sort of canonical min-max methods. Let's see. As far as harmonic maps into the sphere, certainly this construction you aren't getting them, right?
Okay, I see.
I mean, somehow if you have a critical point and you know it's Morse index, then often you expect to be able to do at least locally some kind of min-max construction to say, you know, it sits inside some family such that.
Yeah.
Okay. But in general, you can't make any statement.
But for that specific functional, you don't have that either. It's not like a.
No, you can't say a priori that.
Okay.
That they all arise from a procedure like this. Okay.
Thanks.
For a nice natural one, it's reasonable to expect, though, that there's some procedure like this sitting behind the scenes. Okay. All right, so for each fixed epsilon, we have a critical point with this Morse index bound. But then appealing to these nice results of Fang Hualin and Zhang Wang, which tell you that this is a good approximation from the harmonic map problem, we can say something about convergence. So we can extract a subsequence now as epsilon goes to 0. And then provided n is bigger than or equal to 2, as epsilon goes to 0, we can find a subsequence converging in the following sense. So we're getting in the limit some harmonic map from our manifold M to Sn. And then via bubbling, we could also get a collection of harmonic maps from S2 into Sn, little bubble maps, such that their total energies, the sum of their energies, recovers the min-max energy. Okay? And moreover, their Morse indices, the sum of their Morse indices for the energy functional, as critical points of the energy functional among sphere-valued maps, is bounded above by n plus 1. Okay. Somehow we can pass the index bounds and the energy identity to the limit. Okay.
I'm sorry it's me again.
No, it's great.
Do you know that all critical points are of finite Morse index, or just those obtained by this method, by this min-max?
Yeah, certainly all critical points should be a finite Morse index in this setting if we're just talking about maps from this compact manifold M to Rn plus 1. Yeah. I mean,
okay, thank you.
Basically, your operator is going to be some kind of nice Fredholm operator. Okay. But that actually plays a role in being able to conclude the index results from the min-max construction if we're getting technical. But yeah, it's a nice Fredholm operator regardless of the critical point. Okay. So in any case, we've seen that we have this nice min-max energy, and we can associate it not quite to a harmonic map a priori, but to a harmonic map possibly together with some bubbles. Okay. So just a quick aside, this is all for n bigger than or equal to 2. If we look at n equals 0, so we're looking at the scalar valued case, or n equals 1, the complex valued case, the min-max construction still makes sense. It's qualitatively very different, though. So in the scalar valued case, you can look at these min-max energies E and epsilon. And these were, in fact, introduced by Marco Goraco in his thesis work, okay, where they used an approximation of the min-max construction of minimal hypersurfaces, okay, which has been a hot topic in recent years. Okay, so in this case, the energies blow up like 1 over epsilon as epsilon goes to 0. And critical points are now just these scalar functions, and they're concentrating in the sense of sort of level sets collapsing or energy concentrating along minimal hypersurfaces in M. And these are, in fact, somehow the first min-max minimal hypersurfaces, so the first term in the volume spectrum. Okay, so if M is a surface, and these are somehow the first geodesic networks popping up by min-max procedures. So in this case, it's qualitatively very different. Instead of producing maps from our surface M into some higher dimensional sphere, and now we're somehow producing minimal submanifolds in our surface. But it's interesting that formally the same construction also gives some interesting geometric stuff in this case. And similarly, in the complex valued case, this is something that Darang Chung and I independently looked at in our theses. And in this case, you have energy blowing up like log 1 over epsilon as epsilon goes to 0, and concentration happening along minimal submanifolds of codimension 2. So these are distinguished collections of points in the surface case. So it's kind of funny that in either case, you have interesting geometric objects popping out of this construction. But in these degenerate cases of the scalar and complex valued, you're getting stories about minimal submanifolds inside the domain in question. It's funny that the same construction is popping out. Okay, but back to our world. All right, so we said we have these harmonic maps, but they might have some bubbles. In general, if we're doing these kinds of min-max constructions, we can't expect to rule out bubbles in the general situation. But for the first eigenvalue, for this first min-max construction, that is, it turns out we can. Okay, so where does this come from? So let's record a few facts. Okay, so first of all, it's a result of El-Soufi that for any non-trivial harmonic map from a surface into the n-sphere, the Morse index is always at least n-2. Okay, where the n-2 is corresponding to some two-dimensional equator, which you can push around these n-2 directions perpendicular. Right? Okay, and then by Misha and earlier work on the spectrum of RP2, building on the structure theory of Galavi and Barbosa, observed that if you have a harmonic map from S2 to Sn, so for harmonic maps from S2 to the sphere, there's a very strong structure theory. Then if the Morse index is at most n+1, and you can say more than this, but this is enough for now, then phi has to be an equatorial embedding. Okay. So if we have a low index harmonic map from S2 to Sn, it has to be equatorial. Okay, and moreover, there's this result of the treatise, which is we discussed before in the context of the eigenvalue maximization, right? Which tells us that if M is anything other than a sphere, then this capital lambda 1 is strictly bigger than 8 pi. Okay, so this is going to come up again in our harmonic map construction. Okay, so in particular, let's think about what we have. So we know we have these min-max harmonic maps, Sn. We know the sum of their energies is at least as large as half this lambda 1. And we know that the sum of their Morse indices is at most n+1. Okay, so let's look at this sum of Morse indices statement for a minute. Well, we know that the index of each individual term here, the map itself and each non-trivial bubble, has to be at most n-2. So in particular, if n is sufficiently large, then if we have more than one object here, then we have something like 2n-2 over here, which is going to be bigger than n+1, right? So in particular, as n gets big enough, we can have either just the map or just one bubble. Okay. We'd like to say we have just the map, so let's suppose we have just one bubble. Well, if we have just one bubble, then the second line here tells us that since the Morse index is at most n+1, that bubble has to be equatorial. Okay, but if the bubble is equatorial, then its energy is going to be exactly 4 pi. But that would then tell us that 4 pi is bigger than or equal to half of lambda 1, but we said that's strictly bigger than half of 8 pi, which is 4 pi. So we can't have just one bubble. So the only possibility, once n is sufficiently big, is that we have just the harmonic map. So we actually do get just a nice clean harmonic map coming up from the min-max construction. Okay, so in particular, what have we learned? This tells us that for any conformal structure on a closed surface, as soon as n is bigger than 5, then this min-max procedure is giving us a nice harmonic map from M to Sn, whose energy sits between the normalized first eigenvalue and the conformal volume, okay, and with Morse index at most n+1. Okay. Let's see. So in particular, we started off saying that maximization of conformal eigenvalues gives us these nice distinguished harmonic maps from any conformal class to a higher dimensional sphere. Now we have an alternative construction, giving a nice collection of harmonic maps from any conformal class to a higher dimensional sphere. And the question is, are they the same? Okay. And the big point is that yes, they are. Okay. And somehow the key technical lemma here is that in fact these maps have to stabilize a priori as n goes to infinity. Okay, so I'll state it without proof for now and say a word about the proof in a minute. Okay, but in particular for any fixed conformal class on our closed surface, given a family of harmonic maps with some energy bound, then in fact there's some fixed dimension n depending on the conformal class, the energy bound, such that any harmonic map to a sphere of arbitrary dimension has to in fact take values in a lower dimensional sphere of this fixed dimension capital N. Okay, so if you have a sequence of harmonic maps into spheres which a priori could have dimension going to infinity, in fact they factor through maps to lower spheres of some fixed dimension depending on the energy bound. Okay, so we'll say a bit more later about why that's the case. For now, let's just put it to use. Okay, so we have these harmonic maps that we constructed by these min-max methods. And I'll note that if we take these metrics g bar n defined by half of their energy density times g, so now these are only true metrics away from critical points, but these critical points of phi just correspond to conical singularities in this new metric. Okay, so in this metric, the components of this map Bn are Laplacian eigenfunctions with the common eigenvalue lambda equals 2. That's something you can just check directly from the harmonic map equation. Okay, so the smallest integer k, such that 2 is lambda k for this metric, is called the spectral index of this map. And so equivalently, we're starting from any conformal metric. This is just the same as the index of the Schrodinger operator, Laplacian minus dp squared on functions.
And
right.
Sorry, this time the index is the number of negative eigenvalue when you write it like this?
Exactly, a number of negative eigenvalues.
Okay.
Okay. So in particular, if we're letting k be the spectral index, well then we know that this lambda bar k is going to be exactly twice the min-max energy. Take the min-max energy is the area of this metric. So that's going to be bigger than or equal to lambda 1. Okay, so if we can show that k equals 1, well, then we also know by definition of capital lambda 1 that this lambda bar 1 is bounded above by capital lambda 1. So in particular, if we can show that the spectral index is 1, then that's going to give us equality here. And so we'll know that, that En is exactly 2 lambda 1. Okay, or other way around, half lambda 1. Okay. Okay, so to show that the spectral index is 1 for n large, okay, let's first note that these min-max energies E sub n are decreasing in n. That's an easy thing to check. Okay, so in particular, there's a uniform bound of this energy as n gets large. If there weren't a uniform bound, life would be hopeless. Okay. So by the stabilization lemma, we know that there's then some constant factor, right, depending on that energy bound, such that for all n sufficiently large, these harmonic maps factor through harmonic maps to some lower dimensional sphere, and then just a totally geodesic embedding of that lower dimensional sphere into the higher dimensional sphere in question. Okay, so the idea now is to compare the Morse indices of these maps. Okay, and in this case, the spectral index pops out. Okay, so this is a computation that had come up earlier in some of Misha's work again on the spectrum of RB2. Okay, but you can check that the energy index of this map to the higher dimensional sphere, you can compute it exactly by seeing the energy index of this map to the lower dimensional sphere plus the difference in dimensions of those spheres times the spectral index of the original map Bn. Okay, and this is something you can just check directly by looking at the linearization of the harmonic map equation. It just pops out directly by computation. Okay, but in particular, let's just ignore this middle part for now, this nd of psi n. It follows that n plus 1 is bounded above, is an upper bound for this nd of phi n. Well, and that's then bounded below by n minus capital N, where this capital N is fixed, remember, of the spectral index. Okay, but now as soon as little n is bigger than 2n plus 1, well then this spectral index can't be 2, because we have something 2n is less than or equal to n. So in particular, we see that the spectral index has to be 1. Okay, so via the stabilization trick and comparing the Morse index to the spectral index, we're able to see that the spectral index of these maps for n sufficiently large does have to be 1. And so in particular, we have equality. Okay, so n is sufficiently large. This min-max energy is exactly half this conformal eigenvalue. And this metric that you can associate to this harmonic map is extremal. maybe just a word now about this main technical ingredient, which is the stabilization lemma. Right, so what are we saying? Again, we're saying that we have harmonic maps to spheres of a priori varying dimension, satisfying uniform energy bound. Then, in fact, they take values in a lower dimensional sphere of fixed dimension. So what's the idea? So suppose this weren't the case. Well, then we could find a sequence of harmonic maps into spheres of arbitrarily high dimension, okay, with this uniform energy bound, and such that this Schrodinger operator, for which the coordinate functions lie in the kernel, has to have dimension at least n plus 1, right? Because the coordinate functions lie in the kernel. And so if we aren't lying in some lower dimensional sphere, then this kernel has to have dimension at least n plus 1. Okay. So then the rough idea, which I won't attempt to make precise in this talk, is we can use a variant of standard bubbling analysis for harmonic maps, where now our hands are tied a little bit because we can't appeal to bubbling analysis of the fixed target. But still, a lot of the technology carries through, and we can deduce the existence of some nice positive function or non-negative function in LP, where P is strictly bigger than 1, such that the Schrodinger operator Laplacian minus rho on M union some collection of S2s, okay, has infinitely many eigenvalues less than or equal to 0. Okay, this is coming from this kernel with dimension growing to infinity. Okay, and so this is a somewhat delicate analysis, but the punchline is that we arrive at the Schrodinger operator with infinitely many eigenvalues. Okay, but since rho is an LP for P bigger than 1, we're in dimension 2, that can't happen. Okay, infinitely many eigenvalues below 0. Okay, so this can't occur. So that's the rough idea. Or involves a little bit of work to show. Okay. Questions so far?
So the number of spheres is finite here throughout the process.
Yes.
I mean, this dot 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 is fixed somehow.
Yes, it's fixed by the energy bound. Somehow each sphere you have to lose a bit of energy to get an extra sphere, like a fixed amount of energy. Okay.
Thank you.
Sure. So that aspect is similar to just the standard bubbling analysis. Okay. All right. So this is a cute starting point. So just by classical variational methods for the Dirichlet energy, you get a new proof of the existence of conformally maximizing metrics for lambda 1. Okay, but what can we do with it? All right. Okay, so by definition, this lambda 1 is just the supremum of the normalized first eigenvalue among all conformal metrics. Okay. And with the previous methods for showing existence, they rely on, in some sense, on direct methods where they really are choosing a maximizing sequence of metrics. So with direct methods, it's hard to say, give stronger statements about whether this is supreme among a larger class of objects. Okay. But with our sort of weird method where we pass to this external construction, we're in fact able to say that it's an upper bound for many more things. Okay, so following work of Karev, we can say that given a conformal class and any radon probability measure on our manifold, we can define a generalization of the first Laplacian eigenvalue associated with this conformal class and this radon measure by simply taking the infimum of the Rayleigh quotient, okay, where this Dirichlet energy doesn't depend on the conformal, specific conformal metric. And now we just take L2 with respect to the measure mu and look at all functions with mu average 0. Right, so just the standard one. Okay, and note that if mu is, say, rho squared times the volume, where rho is just some smooth positive function, this is just a first eigenvalue associated with the Laplacian of the conformal metric. So if it's just a nice smooth positive measure, we aren't doing anything new. Okay, but the definition turns out to include a lot of other interesting quantities. So in particular, one that's going to be particularly fun is if we have, say, a surface with boundary. Let's say we normalize the boundary to have unit length. And if we just take the length measure as our probability measure, then this first eigenvalue is going to be exactly the first Steklov eigenvalue. Okay, so it's the first eigenvalue of the Dirichlet and Neumann operator on this boundary, manifold of boundary. Okay. All right, so Kokarev in his work was studying the problem of maximizing this lambda 1 with respect to these measures among all measures. Okay, so it's a slightly, depending on your perspective, weaker or stronger maximization problem. You're allowing this much larger class of potentially much more degenerate objects and trying to see what happens at the maximum. Okay. And so along his way to proving various results here, he observed that the Li-Yao conformal volume bound extends to arbitrary probability measures. Okay, so in particular, the only step that really requires some thought It's just making sure that there's some point in your family where you have zero average now with respect to this new measure, instead of with respect to the Lebesgue measure, right? That's somehow the key point. Okay. And so the observation that's driving our results in this line is that you can replace conformal volume here with this min-max energy, okay, and consequently with this lambda 1. All right, but we have to put a little condition on our measure. So we'll call a radon measure mu admissible if the obvious map from smooth functions on our manifold to L2 with respect to mu extends to a compact map from W12 with respect to into L2 of mu. Okay, so this is going to include things like the boundary, the length measure of curves, which are going to be of interest for studying Steklov eigenvalues, but some degenerate things like Dirac masses don't satisfy this. Okay, but we aren't too interested in Dirac masses, so that's okay. Okay, so the result's then this. So for any admissible probability measure, then in fact the first eigenvalue has to be bounded above by twice this min-max energy. Okay, with equality if and only if mu is exactly one of these smooth measures arising from harmonic maps of spectral index 1. Okay, so in particular, this lambda 1 is bounded above by the supremum over all smooth conformal metrics, and maximizers are given by the energy measure of a sphere-valued harmonic map. So in particular, among these admissible measures, which again includes things like these length measures of curves, you're also getting some regularity statement here. So not only is this lambda 1, not only is the supremum over smooth metrics enough to recover the supremum over all these measures, but you automatically know that any maximizer has to be one of these smooth harmonic guys. Okay, which if you were just trying to develop a regularity theory by the direct method, studying some maximizing sequence of measures, maybe wouldn't be as easy to see this. Okay. All right, so in particular, we're seeing the maximizers of overall measures, admissible measures at least, coincide with maximizers amongst metrics. This is just what I said. All right, so now coming back to Steklov eigenvalues, which we were learning a bit about in Henrik Mathiassen's talk a few weeks ago. So we now see that for any domain inside our surface, it's easy to see that the first Steklov eigenvalue, normalized by its length, is bounded above by lambda 1 of this length measure, normalized by the length. Okay. So in particular, it follows from this result that the normalized first Steklov eigenvalue of this domain is bounded above by this capital lambda 1. Okay. It's maybe not so obvious a priori about this external thing. Okay, so now we note that if we have any metric on a surface with genus gamma and k boundary components, we can always realize this as a subdomain of some closed surface of genus gamma, right? So just take your surface with k ends and glue in disks however you like. We'll get some closed surface of genus gamma. Okay. So in particular, if we let this capital sigma 1 be the supremum over all metrics on the surface of genus gamma and k ends of the normalized first Steklov eigenvalue, then we see that the Steklov supremum is bounded above by the Laplacian supremum on the closed guy of corresponding genus, independent of the number of boundary components, which is a bit surprising. Okay, so at the same time as we're doing this, our fearless organizers, Girouard and Lagacé, showed that in fact the opposite bound holds as k is going to infinity. Okay, so they showed that if you start from any closed surface, then you can always find a sequence of subdomains whose normalized first Steklov eigenvalue is approaching the normalized first eigenvalue of that surface. Okay, which is also surprising. All right, but in particular, combining those results, we see that in fact we take the limit as k goes to infinity of this sigma 1 of over surfaces of genus gamma and k boundary components, then we in fact get exactly the normalized first Laplacian eigenvalue of the closed surface. All right, and I mean this is pretty interesting on its own, but in particular in recent years, following the work of Vailana Fraser and Rick Shane, there's been a lot of interest in the study of maximal metrics for these normalized first Steklov eigenvalues, because Fraser and Shane observed that these maximal metrics are induced by free boundary minimal immersions into Euclidean balls. Okay, and so we were hearing a lot about this from Henrik a few weeks ago. And in particular, Mathiassen and Betrides have now shown that in fact these maximizers exist, these topological maximizers for Steklov eigenvalue for any genus and number of boundary components. Okay, so in particular, they're going to be producing free boundary minimal immersions into the ball. And what this identity here tells us is that for fixed genus, as we take the number of boundary components going to infinity, the areas of these distinguished free boundary minimal surfaces of genus gamma and kns is converging to the area of the closed surface in the sphere of genus gamma, corresponding to maximization of the Laplacian eigenvalues. Kind of striking. Okay. All right. So I'm running a little long, so I'll be somewhat brief about the second eigenvalues. Okay, but take a lot of intuition from arguments that Nadarashvili and Dirichlet use to characterize lambda 2 of S2 as the union of two round spheres. We're going to define this collection for the second eigenvalue of weakly continuous families. Now they're going to be two n plus 1 parameter families from the product of the n plus 1 ball with itself. And I'll make this definition in terms of weakly continuous families of sphere valued maps, but then in practice we define these via this modification as before. Okay, so the boundary conditions we put on this case might look a little strange a priori. So on the part of the boundary that's Sn cross Bn plus 1, we just require that this A point in the Sn is taken to itself. Okay, so on that part, we just look like the same boundary conditions we had for the first eigenvalue case. Okay, on the other portion of the boundary, the Bn plus 1 cross Sn portion, we're sending FAB, and we're saying that's going to be the same thing. We're imposing a little symmetry here as, okay, so tau B is going to denote reflection through the hyperplane perpendicular to a point B in Sn. Okay, and so we say that FAB has to be the same thing as the composition of tau B with the map F associated with the points tau B of A comma minus B. That looks strange for now. Just note that we're imposing some symmetry that's going to be helpful later. Okay. And again, this is going to come from work that Nadarashvili and Dirichlet. Okay. Okay, and then roughly we just define En2 to be the min-max energy over these families. Okay. All right. So the key point that we want to establish, right, is that this is an upper bound for half of lambda 2. Okay. So what's the idea? So given any metric, let's fix the first eigenfunction, B1, first non-trivial eigenfunction. So before we just wanted to know that we had a map with 0 average. Now we want to know that somewhere in this family, we have a map that has 0 average, with respect to the volume measure, but also weighted against this first eigenfunction. All right. So if we define this map I from sending AB to the average FAB over the volume and average with respect to this first eigenfunction, we want to know that that has to have a 0. Okay, so indeed, if it does, then the same Hirsch trick from before is going to tell us that our energy is an upper bound for lambda 2. Okay, so the idea is suppose it doesn't have zeros. Okay, well then we can use this. Let me skip through some of the notation here. We can use it to define a map from the 2n plus 2 ball to the 2n plus 1 sphere. Okay, and on the boundary sphere, so on the boundary, this is going to define a map from 2n plus 1 to itself, S2n plus 1 to itself. Okay, since it extends to a map inside, it's going to have to be null homotopic, but we preserve the symmetries that we imposed on our families at the boundary. Okay, so those symmetry conditions are going to force this map from the 2n plus 1 sphere to itself to have fixed points that come in pairs. So we have an even number of fixed points. Okay. Okay, but we have this Lefschetz-Hop fixed point theorem, which tells us that for a generic, where generic is some transversality condition, a generic null homotopic self-map of the sphere, then the number of fixed points has to be odd. Okay. So in particular, if we have an even number of fixed points, we can't be null homotopic, which then tells us that this map couldn't extend into the 2n plus 1 ball, which tells us that our original map we're looking at has to have a 0 somewhere. Okay. So in particular, we have to have a map somewhere in our family which has 0 average with respect to both 1 and the first eigenfunction, and so we have this desired lower bound. Okay. So where are these boundary conditions in these families actually coming from? Well, again, they're coming from this construction of Nadarashvili. So let's just construct one family to see at least that this min-max energy is well-defined and not infinity, right? Okay, so how can we construct such a family? Right, so the idea is we take FA sub B. So let's fix again. Let's start out by taking a branch conformal immersion from our surface into Sn. Okay, now we compose it first with these maps, which are defined by fixing some spherical cap, okay, and acting on its complement by a conformal reflection. So we're pushing all of the sphere into this fixed spherical cap. Okay. So that's this middle composition. And then on the end, we're just composing again with this n+1 parameter family of conformal dilations. So we have this branch conformal immersion that we're composing with one n+1 parameter family of maps and another n+1 parameter family of maps. And it turns out these are going to have uniformly bounded energy and have the desired boundary symmetry conditions. Okay, and in particular, you can actually show now that this min-max energy is not only finite, but it's bounded above by 4 times the n-conformal volume. Okay. And now somehow the same analytic machinery we had before carries through. The analytic machinery isn't really sensitive to which eigenvalue you're looking at. Okay, and we can say that for any closed Riemann surface, and n sufficiently large, there exists a harmonic map such that one of 2 things is the case. Either we have a harmonic map achieving this min-max energy, a Morse index at most 2n+2, or we have a harmonic map together with a geodesic equator. So an S2, we can have a non-trivial harmonic map from S2 into Sn sitting alongside us this time. So we have a harmonic map together with some equatorial bubble. And we don't expect to rule this out in general because we know that for maximization of higher eigenvalues, we have bubbles occurring, right? So we can expect either case to be a possibility. Okay. And then by the same stabilization lemma and the same kind of machinery as before, we're able to show that as n gets sufficiently large, then in fact these do coincide. So in either case, we can apply the stabilization argument and see that the min-max energy has to be the same as the normalized second eigenvalue. Okay, so then all of these applications go through as before, with the first eigenvalue replaced by the second. Okay, so we can say that this is an upper bound for lambda2 of any admissible probability measure. Okay, inequality only for energy densities for harmonic maps of spectral index 2. And similarly, we can get these upper bounds on the second Steklov eigenvalue. Okay, and again, results of Girouard and Lagacé don't depend on, they hold for all eigenvalues. Okay, so it's those hold also for the k=2 case. Okay, I'll just mention that we expect that similar min-max characterizations should be possible for the higher eigenvalues. And if that's true, then the same applications to the Steklov eigenvalues and the lambda k maximizing measures, they should all go through. Okay, but that's somewhat speculative. So thanks very much for your attention. Okay, that's it.
Thank you very much, Daniel, for this very interesting talk. It's now time to take questions. If some people have questions, please, I think I asked mine, but go ahead if you have questions. Do I hear a question here or do I hear someone? Is someone asking a question? Okay, so I have questions. I can start. Do you know if any of this could be salvage in dimension larger than 2?
Okay, that's a big question.
Yeah.
Interested in. Yes, I mean, a fundamental problem, right, that distinguishes dimension 2 from higher dimension is that the Dirichlet energy is not conformally invariant in dimension larger than 2, right? So yeah, there's a natural analog of these things one could look at, where instead of looking at harmonic maps, you're looking at so-called n-harmonic maps, right? The critical points for the Ln norm of the gradient. And somehow a problem here, which shows up, I think, in as far as I can tell, in any approach to these conformal maximization problems in higher dimension, is that when you make a conformal change by a degenerate conformal factor, one with some zeros, right? Then somehow the elliptic equations you're looking at cease to be elliptic, right? You get now this conformal factor is showing up not only in some potential of some Schrodinger operator, but in the actual principal part as well, and destroying your ellipticity. So you really need a good understanding of the zeros of your conformal factors, you know, and in the case of this n-harmonic map approach, you know, what the critical set looks like and how badly it destroys the ellipticity of your eigenvalue equations and these kind of things. So So I think there's hope that there's a tremendous amount of analytic work to be done to make it work.